Mm, okay. So is the slide visible?
Yes, sir.
Okay. So we were talking of what? Just a minute, I need to go back. Yes, this thing. So this heavy tail behavior is quite natural. This, even in the occurrence of COVID, this rare event, it's also chances of having a COVID pandemic in future. So what do you think? Should it be modeled by light tail distribution or heavy tail distribution? The events like COVID. What is your viewpoint?
Lightweight.
Because if you use lightweight, then the extreme values, or the values which will have high impact, you cannot give them probability, high probability, so they cannot occur. So if you assign a significant event like blue line, the blue line is light tailed, so then obviously then the events like COVID you cannot model them. Then you need to use some heavy tail model, heavy tail distribution to model events like COVID, because these events are occurring, and they occur very rare, but when they occur they make a quite big damage, because the x-axis, think of the x-axis as a damage level, that 0 2 4 5 6 8 10. This is some damage level or number of deaths or whatever you can say. So which a pandemic is causing. So a light tail distribution always assigns a very low probability or near zero probability to the extreme values, or the values which cause damage. So it means that the light tail distribution like the blue one, they fail to model uh, uh, just like, because why we fail to predict such a pandemic as COVID, because the pandemic guys, they were using light tail distribution, they were not modeling the pandemics in the entire world by using the heavy tail distribution. If they have, then obviously they would have predicted that chances of having a big pandemic can occur, which can have significant damage. Just like you can see the red line is assigning more probability in the tail behavior, because you know that unfortunately we our scientists, our researchers focus more on the body part of data, the main part of data. They do not focus on extreme values. The modeling of extreme values has been ignored. It's an ignored area. It's true. So and I would say that very few researchers in some areas, they always work on extreme values, like people in earthquake engineering, they work on extreme values. But unfortunately in internet modeling and other kind of data scientists, very few researchers, they work on modeling of the extreme events. So these extreme events, I mentioned COVID as a good example, and same events can come in internet traffic, and you can have a big DDoS attack kind of thing. So that's why. So that's there comes the importance of heavy tail distributions. So this is a simple test which we discussed last time, that if you have a data, so just plot the log of 1 minus fx, the complementary ccdf versus log of data. If it is straight line, then it means that your data has extreme events. Your data cannot be modeled by a light tail distribution. Your data will be modeled by a heavy tail distribution. And it's also indirectly means that your data will have extreme events. So I think this is just a review of that historical review, that in 1985 the computer system workloads variability that showed the heavy tail behavior. In 1985 to 1992, the file size distribution was also found to be heavy tail. The process lifetime also found to be heavy tail. It means that they were mostly small sizes, but finding a file which is very big in size is also there. So you cannot ignore a file which is very big. And same is with attention and polynomial tail shape, heavy tail. And since 1998, they use internet modeling, they used standard models. So this is the formula, probability that x greater than x equals to nearly equals to x to the power minus alpha. And we had some discussion on the behavior of alpha, that alpha controls, this is a very simple equation. Any engineer or any basic guy understanding about basic probability should understand the power weight equation. That you see, you should understand that what's the power weight equation, what it means. That probability that random variable x, a capital X is a random variable, okay, it can take shape any value randomly, and a small x is any given value, which we use on x-axis is x to the power minus alpha. So you can see that this alpha behavior, if you plot this behavior on graph, so you can see that this alpha controls the tail behavior of this distribution. If alpha is very near to zero, then obviously the probability will increase. Okay, and if alpha is very high, for example, if x to the power minus 100 or x to the power minus 1000, what will happen? If alpha is 100 and alpha is 1000, and you keep increasing alpha, so what will be the impact on this probability? If you keep increasing alpha, what will be the impact of the probability? Probability that capital X, random variable x, greater than small x. So can you tell me, anybody one can tell me, increasing alpha will have what impact?
So probability will decrease.
Yes, a
Probability
decrease
will
in probability.
decrease, because x to the power minus 100, it will be 1 upon x to the power 100. So then obviously it will, the overall value will decrease. Okay, but what about if we choose alpha very near to zero, like alpha point 0.1 or alpha
Probability
point,
maybe one
prob probability will,
or
I
one
mean, we can,
or increase.
it will increase, but obviously it cannot obviously, what about if alpha is equals to zero? What about alpha is equals to zero? If alpha is equals to zero, what will happen?
So probability will
It equal
become
one.
100%.
It will be,
It
because
is
if you take alpha is equals to zero, then x ki power minus zero, and x ki power minus zero minus into zero zero, x ki power zero is equals to one.
1.
So it means that that then you see that what will be the impact, that probability that probability that x, random variable x is greater than x. Okay, so then answer is, if alpha is equals to zero, and this is just a test case for you to understand. You said that alpha is equals to zero. I asked you the question that if alpha is equals to zero, obviously then x to the power minus zero, it will be one. So probability that x greater than, can you see my mouse?
yes, sir.
Yes,
This
sir.
whole thing will be equals to one. It means that probability that x greater than small x, first of all, in case of alpha is equal to zero, it will be independent of x. So it means that whatever the value of x is, the answer will be
One.
one. So can you see the significance, that whatever the value of x is, if alpha is equal to zero, the answer will be always be one. So can you think in terms of probability, that random variable x is greater than x, okay, and the answer is always one. What can be the case? What it is saying, that a random variable x, and you are interested in analyzing the tail behavior, because this is the formula for the heavy tail distribution. If it shows that capital random variable x, it can be your packet count data. Capital X can be your packet count data. It can be your any type of byte count data. Okay, so if packet count data is greater than x is one, so it whatever value is smaller, or so it shows one. So obviously it means that whatever value of packet count occurs, the probability of that random variable will always be one. Okay, so this is showing the completely extreme kind of behavior, that whatever your random variable is, I mean, it will be always greater than whatever value you say. I mean, this is whatever value you choose. If you choose a small x, for example, if you choose a small x is 1 million or 10 million, so high value of this. So what will happen? So any value you choose a small x, then answer will be always 1. It means that your packet count data, your byte count data, whatever it is, it will be always greater than your specified value. So that's a stochastic behavior which we need to understand. And then try to, and then obviously when you increase alpha, then the probability will decrease. So the near the value of the less the value of alpha near zero. Okay, we cannot take it zero, because zero is, you say, is very unrealistic, because for zero, alpha is equal to zero, then it means that all the probabilities will be one, irrespective of your whatever the value, the given value. The small x is the given value. So that's why. So you can easily plot this. Okay, so I can even try to show this, that how can I show this? I can just stop sharing, because this is something important. Sorry, there's too much noise in my street. You have to bear with this. Can you see this whiteboard? Can you see this? Can you see this, what I'm writing?
No, sir.
Uh, I tried to share the screen. Let me share again. Mm. Can you see now?
Yes,
Yes,
sir.
sir.
Okay. So can anybody repeat what was the formula? Probability. Sorry. Probability that random variable capital X is greater
Greater
than
than
small x was equals to x ki power minus alpha. Okay, so we were commenting on, because this alpha is it controls your tail behavior. If alpha is equals to 0, so what will happen? Probability random variable capital X, it can be your packet count data, it can be your byte count data, whatever variable you are investigating, is greater than because you can see that it's analyzing the tail part, because whenever there is a value greater than, because it means that it is looking at the right side of the density function. So that means x ki power minus 0, and obviously this is something close to 1. So independent, so you can see in the answer we are not having x. So it means that if we plot this value, this is your small x values, and obviously these are the random variable capital X. It can, because this think of, because some of the people do not understand what's the probability. This random variable capital X, it is this small x. It can take values, it can take values 0. Okay, it can take values 1, whatever the values in terms of your data, 1000, 2000. So the small x is just a realization of this capital X. Capital X is a random variable. Why we call it random? Because small x changes. So now this is the sorry. So this is probability that x greater than small x. So this is 0. This is zero point 0.5. This is 1. So in this situation, when alpha is equal to 0, what will happen? The answer is, what will happen? It is
The
straight line.
probability is yeah.
Because why straight line? Because in the answer there is no x. So because this is the answer, probability capital X greater than x, the answer is always 1. So whatever, so if for the small values of small x, the answer is probability is equals to 1. For medium values, or even for very large values of small x, still the answer is 1. So that shows that this probability is now independent of whatever value you have. So it means that your random variable x, whatever value you choose, it will always, the probability of random variable x uh, will always be greater than whatever value you specify here. It will always be greater than that. That shows that this is the behavior. So then obviously this is not modeling our required part. Same is the case when we take uh, alpha, for example, very high, 1000, alpha 1000. So what will happen? So that will probability x greater than x is equals to x की power, sorry,
Near zero.
mm, x की power minus alpha 1000. So this will be 1 over x 1000. Okay, so obviously this will in the denominator value will increase, and then obviously this will decrease the chances of the rare events. So obviously this will so we can say that that this is a small x, and this is probability that x greater than x. So if this alpha is very high, it means that it will fall very quickly. Okay, but when alpha is very small, like if alpha is equals to let me show it here. If alpha is equals to uh, zero point 0.1, then obviously probability x greater than x की power minus zero point 0.1, or this will obviously 1 over x की power 0.1, then obviously this value will be quite near to 1. So this the probability, this is the x, and p x greater than x. So this thing will be very, this is 1. So this will you can see that this will decay very slow. So the higher the values, the more the chance of this heavy tail behavior. So this is just the way you should understand the power tail. So coming back, that this equation, like I should signify that this equation is key to understand the main thing, and you should know the behavior of this alpha. And then let me warn you in advance that for alpha value 0 and less than 1, there are two very important ranges, and especially in case of the data, when you generate data like this, then mean is infinite, because if the mean is infinite, then obviously the variance will also be infinite. Okay, and in this case, uh, when alpha is between 1 and 2, okay, then mean becomes finite and variance is still infinite. So this is the case. So you should note down this thing very clearly, and then I will prove it mathematically, that how, what's the meaning of infinite mean and variance. I think in the last class I tried my best to illustrate you what is the meaning of infinite mean, what is the meaning of infinite variance. I would repeat that if the mean is infinite, then obviously you generate more and more data, the mean will never converge. And I think that the very strong example of this is, let me come back to the slide here. Sorry, I need to open the slide. Can you see the slide?
Yes, sir.
So
Yes,
this
sir.
is, so here, what is the value of alpha? What is the value of alpha here?
0.8.
0.8. Okay, and on the left plot is very simple. Left plot is just observation on the x-axis and the value on the y-axis. So here it shows the data which is coming from a distribution with power tail, the same formula, with alpha is equals to zero point 0.8. So you can see that most of the values are lower values, but you can see I can see at least 1 2 3 4 5 6 to 7 big peaks. Okay, so these are the big peaks. So what is the meaning of because when alpha is equals to zero point 0.8, then it means that the mean is infinite and also the variance is also infinite. So you can see that when you compute the running mean, the running mean of such data, you can see on the right side is just the same observation, and we just compute the running mean, the moving average of the data, which is shown on the left side. It's a very simple graph. So you can see that how drastically the mean changes as any student of basic math knows that when we start increasing the number of observations in the same data set, the mean value converges. The mean value converges. It does not deviate. But you can see that here the mean value is deviating too much. And obviously, what is the, and it never, even at 6,000, 8,000, 10,000, you can see that the mean value is not getting stabilized, although you are getting more and more data set. So can anybody tell me the reason that why mean value is not getting stabilized despite the fact that uh, we are increasing more, we are taking average on more and more data points?
So because of extreme value.
Obviously, because your data set has extreme values. Okay, so in normal distribution we do not have extreme values. This mean value will have to, this mean value will just look like, if you can see the movement of my mouse, it will start from 0 and then it will just take jump to the value. For example, the actual mean is 3.7. You can see the movement of my mouse here. So the mean value will just try to converge near 3.7, whatever mean value is. If mean value is 1000, so it will just data will jump to the 1000 and then it will oscillate, and then as soon as you 2000, 4000, 6000, you can see on the x-axis, the more the value you get, the more your mean value converges. And in case of heavy tail data, this is quite obvious that your mean value never converges to a single value. It keeps oscillating, and if even after 10,000, it can jump to another value. And obviously, that's due to these spikes totally disturb the these spikes totally disturb and upset the mean behavior. So that's why mean never converges. So that is the real challenge in the modeling of such data set, because the modeling of such data sets is cannot be done very easily, because you can see that there are many distributions which take mean value as a parameter. Most of the distribution take mean value as a parameter for modeling of data set. But how come here in this case we can give the mean value as a parameter, because the mean value is not representing the data itself? And I think that we have so many experienced fellows sitting in the class. You can give me many examples in which mean value does not represent the actual data. Can anybody in this class tell me more example that where the mean value does not represent your data? Although you can compute mean value, this you can compute mean value. A classical example I showed you, that the mean value shown as shown in your firewall graphs in your NMS, uh, which captures the mean, the running mean of internet traffic, the mean value, the user behavior. Okay, it shows then it is not representative, because internet traffic has the similar behavior which is shown in this plot, the left plot. It has peaks. So this type of data set can never be described by mean value. Even variance cannot describe the value. It cannot be parameterized. I don't think that there are many physical phenomena in this world uh, in which the mean value never represents your data set. Although if you compute it, it will mislead you. So can you think of more examples in which mean value does not reflect your data set? Okay, any other example where such kind of behavior, you are seeing the graph here, the left graph and the running mean on the right graph, and the alpha is zero point 0.8. So So I am asking examples in which this kind of behavior fits. Any idea? Okay, let me give you a hint. Examples from, I would welcome examples from finances, financial systems.
So stock exchange, trending
Stock.
graph.
Stock exchange trends, yes, because they also have a great variance. You cannot just represent a daily stock trend by having a single mean value. It will obviously, anybody having basic understanding of a stock exchange will laugh if you tell you, okay, the daily mean today is that value. They will have, they are different parameters. They choose maximum value to quantify their performance. Not mean value. And any other any other example other than a stock market? I think there are many in natural sciences. There are many examples in which such kind of behavior, like I've already mentioned that the file size in computer system is the. I think I was reading that the node degree distribution of internet has also similar distributions, and also the friend request pattern in Facebook also follow the such kind of behavior, the habitual behavior in terms of topology, the friend request pattern of because most of the users, they have some friends, and then there are some celebrities which are getting thousands and thousands of friend requests daily, and then Facebook will have to model such kind of data uh, to provide connectivity patterns. And for example, if I'm a celebrity, I got 1 million friend requests. So obviously Facebook will have to place my profile such a way that in such a data center that the latency to uh, my clients is reduced. So Facebook clearly always I was reading a such paper in which Facebook migrates your profiling servers with respect to the popularity of the person whose account is. So this kind of behavior is being already monitored, and the research is quite useful research for the performance modeling and capacity planning. Okay, so any other example in which, I'm asking for examples for data in which there's very high variance data. You can search on internet and then tell me, okay, what's the example of high variance data in which there is the data is natural, but it has so much high variance that mean value cannot accurately describe your data set. Any idea? You can search on internet and then just tell me that. Um, okay, let me Google out. Not helping me. I have to Google out myself. Data examples. I see that the snow pattern, the snowflake, is an example of such data. The boundary of sea has such data distributions. So there are so many examples you can describe by using mean value. Okay, so coming back to this, uh, can I see the current slide now? Okay, can you see the slide?
Yes, sir.
Yes, sir.
The autocorrelation?
Yes, sir.
Hmm. Okay, so once we have characterized the marginals, so I think we have done it. So this order. So this is the formula for the autocorrelation function ACF. and it assumes your data is stationarity. Okay, so the rk is the autocorrelation function. You can see that is the expected value of xn, and then n is your running index, and that plus k is the lag value, that how much far your data point is from current value. If you remember that correlation is something, relationship between two variables, and autocorrelation is something dependency of in single variable. Okay, so we just check value at xn, and then value at xn plus k, so how much it is correlated. For example, in this graph, it is showing that you can see that there exists a lot of correlation at lag of 0 and then 1, and then and they start decreasing, so that shows the dependence pattern of the data in the same time series. Okay, and what it shows here, that at lag 0, obviously at lag 0 the value will be always, always the same. So at lag 0 your data is always correlated, whatever value is there, at lag 0 it will be the same value. So it will always be, its auto correlation function is always 1 at lag 0. Okay, so coming back to the point that why internet traffic is so much heavily dependent on IP. Obviously, we all know that internet traffic is the main governing protocol is IP, and then TCP at transport layer, and also UDP at transport layer. Client request server, and then response comes back to the client. So network traffic overall is superposition of flows. Okay, it can be TCP flow, it can be UDP flow, and that superposition occurs at not at a single point. It occurs at switches first, and then routers, and then tier one routers, and it goes on and on. So superposition level also plays a significant role in modeling of internet traffic. In access network, there's a lot of superposition going on at switches. In backbone core networks, there's a lot of superposition going on. In in routers, there are less links, but there are more traffic load. So how does autocorrelation arise in case of internet traffic? So one of the reasons why flows sources appear to be on off. So this is just a modeling of flows, that how can you model an individual user. So individual user can this is the on period, you can see, and off period. Okay, so p1, p2, and p3, these three are the three different users, and obviously their traffic is coming, and then you get such process is get superposed, and source appear to be on off model, whatever we do. Because at the moment I'm speaking and you are silent, most of the traffic is coming from my machine to your machine. uh, you are not speaking, so that's why you are in a silent mode. Okay, you are just receiving my data, so I'm in on mode. At sometimes I ask question and I keep silence, and then I'm in the off mode, and then you are in the on mode. So here the idea is that in the on mode, some of the researchers has assumed that the traffic pattern is CBR, constant bit rate, and the other researchers have obeyed more realistic data, that it follows some kind of data distribution of rate distribution. But at the meantime, what I would tell you is that if the duration of this on period and off period, if if this duration follows heavy tail behavior, because we have just seen in detail what do you mean by heavy tail behavior. If this duration, the duration of on period and duration of off period is follows heavy tail, what does it mean? If the duration of on period heavy tail, it means that most of the on periods are small, 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 and then there are very, very high distribution, and the distribution of off period is heavy tail with certain value of alpha. And obviously when we say heavy tail, then obviously alpha will be between 0 or 1, or between 1 and 2. Greater than, if alpha is greater than 2, then there's no concept of heavy tail. So that's why I keep advising you that you must investigate the value of alpha. And I can tell you one thing, that one of my PhD students, she is working on the sequential estimation to find the value of alpha from real data. So that's a really challenging problem. In your case, I'm not going into the research details of alpha, but you must know the significance of alpha. The more the alpha is close to 0, the more the tail pattern, the more the data will be heavy tail, and the more the chances of rare event will be in your data set. So here, if the duration of on and off period follows in heavy tail distribution, and then we multiplex such kind of traffic, and obviously this will result in more and more correlation. So this is the okay. Um, so can anybody tell me why that if P1, P2, P3 we multiplex them, and then on and off period uh, is heavy tail, then why this multiplexing will result in dependent traffic or which has high correlation, how high autocorrelation? Because alternatively, I'm saying that if the duration of on off period is your think time, because if you're browsing, then you're thinking on a web page, then off period is your think time, and on period is your data transfer time. Okay, so what if this is it on and off period follows heavy tail, then why if we multiplex them to p1, p2, p3 and so on, so why if we multiplex such data, it will result in uh, correlated traffic, or there will be dependency, it will not be like a smooth traffic. Even I think you can justify think about that, if we multiply such traffic, will it be smooth, or will it not be, because if we keep increasing number of sources with such traffic which is shown here, so will it get smooth, or the variance will keep increasing? Any answer?
Ratings will increase.
Where only when you must say that if we increase p1, p2, p3 number of sources to infinite, and then the distribution of on and off period, or your think time period is infinite, then it will result is in a, it will, such a proposition will never lead to a smooth traffic. It will always lead to busty traffic, irregular traffic, which is correlated. But if the think times on and off traffic, they are not so much variable, the value of alpha is greater than 2. Okay, so the on and off periods, they follow a light tail distribution, then ultimately such superposition will obviously generate more traffic, but the resulting traffic will be smooth. It will not be busty, it will not be correlated. So that's the reason. So, and I think that you might be getting idea when you add random variables together, so what should be the impact? Normally superposition and adding, you must remember that whenever that I think that just tell me an example that there's a what's the busiest road in Karachi?
Sharaf Hassan.
Sharaf has
Smooth or busty, or what is always congested?
said you can say always busy.
Always congested.
Always in terms of traffic, what should I say? It is smooth, because if I say that traffic at Shara Festival is smooth, sorry, it's bursty. Bursty traffic means that there are long gaps, and then there's a big burst of so many cars, and then the Shara Festival is getting empty. Okay, and then the big burst of so many cars. So bursty means, because whenever your data is correlated, then it means there are burst in your data. There's burst because correlation generate burst. In case of smooth traffic, there is no burst traffic, although traffic is high, but and as you already said that Sharafasar is the busiest road. So I think that there are many small roads multiplexing to Sharafasar, coming at Drig Road or other location. There are so many coming from other places. There the small roads are multiplexing at a big road, Sharafasar. So the same problem and always arises in road planning, road engineering, because this is also a discrete study which we are focusing on. And in case of urban traffic engineering, they have the same discrete problem, that how to do the capacity planning of roads. So the link capacity planning and road capacity planning suffer the same, they share the same parameters, that how to, if the incoming traffic is bursty, then what should be the road behavior of the multiplex road, So if you are saying that Shara FSL is always smooth traffic or congested traffic because there is not big variance, then what should be the traffic pattern of the link? Would it be busty or not busty? Because this is the question which civil engineers asking. I think you can see that this is the superposition of on-off sources. So you can see this the autocorrelation behavior that what it does. Let me screen more clearly. Mm, So I think you will understand more when we see that traffic patterns on a link are strongly affected by two factors. We have discussed about the amount of multiplexing on the link, essentially how many flows are sharing the link, okay, and where the flows are bottleneck. Is each flows bottleneck on or off the link, and do all the bottleneck have the same rate? Okay, so these are the two factors which strongly affect the traffic patterns on the link: the amount of multiplexing and the flow bottleneck. And these are some of the data sets is shown here of the low multiplex traffic. So this is the graph in blue is showing the number of bytes on the y-axis and the time unit time. Okay, 0 and 2000 to 4000 and 6000. So this is the number of bytes received at certain interface. Okay, so you can see that there are what kind of correlation pattern is there, and the similar pattern is shown in here, number of bytes, okay, and on the right side. So the autocorrelation function is low here, and this is the example of highly, so this is the case of the traffic when it is low multiplex traffic. Okay, the level of multiplexing is low. Can you see the blue graph here, the top one? So it is the example of low multiplex, and this is the example of highly multiplex traffic. So what a difference you can see. I want you to quantify, don't ignore the other graphs. I want you to see this graph where the level of multiplexing is low, okay, and see this graph where the level of multiplexing is high. Okay, so I want you to discuss the modeling of both. So this is uh, the road where there's less multiplexing. You can see and this is the road where there's high multiplexing. So I need you to understand the example of that Sharaf SL. Is it highly multiplex road or it is low multiplex road?
So it is highly multiplex.
Highly multiplex.
So if this highly multiplex load, so okay, so you said that Sharaf SL is highly multiplex load, and this is the graph of that blue graph showing the highly multiplex link. Okay, so the traffic pattern is like this. Okay, so and this is the graph, the previous graph, low multiplex traffic. So can you tell me which one is more smooth?
The high multiplex.
Highly multiplex traffic.
Highly multiplex traffic.
Highly multi traffic is more smooth, and if you agree that this is more smooth, then it means that the can we explain this traffic with some mean value?
Yes, sir.
Yes, and going back, can you see the previous graph now, low multiplex traffic? Can we explain these values here by taking the mean value?
No, sir.
No.
Obviously, because there are so many peaks there, and then obviously this is you cannot represent, so that can be modeled by a heavy tail distribution. Okay, because there are more rare events, there are more peaks. Whereas when the data is highly multiplexed, then It means that the mean can represent your data. Almost, although mean value is quite high in this case, but the thing is that the the traffic pattern got smooth. Okay, so and if you multiplex more and more such kind of traffic, it will get more and more smooth. So this phenomena is called as in traffic modeling, it is called as multiplexing gain. The more the traffic you multiplex, it will get more and more smoother. And obviously this is the behavior which every common person like me and you observed that when we multiplex such kind of traffic, uh, it will increase of multiplexing level will cause traffic to get smoother and smoother, although the road will be maybe a congested the thing, but the level will be smoother. It's true, but the thing is that sometimes it does not happen. Sometimes it is true that sometimes even highly multiplexed traffic or highly multiplexed links can show a behavior which is look like this one, this one in which we can have a big peaks here. So that's why. So in that case, there is no multiplexing gain. So you should understand when you get a multiplexing gain and when you do not get a multiplexing gain. This is the case of this is a normal case, low multiplex traffic, and then highly multiplex traffic. So that there can be case when even if you multiplex level increases, then your the variance here, the mean value doesn't cannot represent your values. So this is the ACF function of highly multiplex traffic, that shows the autocorrelation function is decaying. Okay, and this is just showing the byte part of that highly multiplex traffic. This because it's totally random. Okay, so this is just showing the variability in correction rates. Okay, low rate is equals to beta and high rate is equals to these rate parameters are due to this. So uh, in this case we are just revisiting that on and off model. So you can see at the bottom of the page this that now there are two types of possibilities result in such kind of multiplexing. Okay, so can you see the both parts separately? Can you see this both multiplexing diagram?
Yes, sir.
Okay, so so you can see that a low rate traffic, and on the right side is a high rate traffic, and the high variability in connection rates, RTTs. Okay, these are the connection rates. Okay, so you can see on the left part and the difference on the right part, that's the multiplexing at the left side. If you add such traffic in which on and off duration, uh, okay, as a low rate, so you can see that what is resulting in here, it's a process called as fractional Gaussian noise. And then on the right side, when you multiplex such kind of busty traffic, okay, so you add such links together, and then you got a new process, the stochastic process called as stable Levy noise. I think you all must have studied about the Gaussian motion in your matriculation or something. It's a limiting case of Brownian motion. So it's a Gaussian noise, fractional Gaussian noise. So these are the two very important stochastic processes. I think that I will explain more on this mathematically. How can because at the moment we cannot just say by this diagram, but you need to just note down two important stochastic processes. One is fractional Gaussian noise, and the other one is stable Levy noise. So just see this Gaussian noise looks like this. This is smooth, it's totally random traffic, and the stable noise is just like this. So if your after multiplexing your traffic has jumps, so many jumps, so what type of process you will use, Gaussian noise or Levy noise? Just be generic, any type of data, it if it has jumps, so what you will use, the fractional Gaussian noise or stable Levy noise?
Sir, the Levy noise.
Yeah, because Levy noise, you can see that in Levy noise there are significant jumps. Okay, the fractional Gaussian noise, it's although there is so much, it's a big multiplexing level involved in there, but the traffic pattern is fractional Gaussian noise is smooth, and there may be hidden correlation in the data set. Okay, but overall it's the behavior is Gaussian, and obviously we all know that a Gaussian process is easily described by mean value and the variance. But in case of stable Levy noise, there are so many jumps. So internet traffic can be described by fractional Gaussian noise. But if there is some attack pattern or some anomaly or some DDoS attack, then internet traffic will never behave like fractional Gaussian noise. It will behave like
Stable Levy noise.
stable living noise. So this is the kind of research issue that why we do traffic monitoring. That we do traffic monitoring so that we do traffic modeling, especially that most of us and most of the network operation guys will think that, oh, this discussion is going stupid and why we do this. But the thing is that the reality is that if you do traffic modeling, then that will help you to detect any kind of anomalous condition. If you capture some traffic during a half an hour period, and then you got a time series data, and then it's resembling fractional Gaussian noise, so then that means that it's okay. But if it's behaving like a Levy process, then it means that there's something anomaly. So this is just I would call as a researcher, as a privacy preserving method to detect the DDoS attack. That the In order to differentiate between a normal traffic and a malicious traffic, you must know that the traffic model should be Gaussian or should be stable Levy noise. But unfortunately, there are cases in which such kind of modeling can lead to false positive. For example, internet traffic at certain situation is behaving like this, and then Pakistan won the match. So what will happen in such kind of, is such there's some football match or some there's a result announced. So such kind of events also trigger anomaly. They cause that the time series behavior to drift. So in such a case, you can a normal traffic can exhibit a normal traffic which should be fractional Gaussian noise behavior. It can exhibit stable Levy noise. So in that case, your modeling can lead to a false positive. So that's a research challenge, so that you should not when you model a traffic by Levy noise, then because it's Levy noise has so many jumps, it can model so many jumps, anomalous jumps. So then it means that you need to be careful in modeling. So I hope that you got some idea that what is the importance of traffic models. Okay, any question till now?
No, sir.
Another RK, uh, and you can see that long range dependence, LRD. Okay, so LRD is there are two ACF graphs in this slide, in which the left one, the ACF function decays very quickly, and the right one, the ACF function, the autocorrelation function, I mean the dependence of variable within inside. And if you don't remember, the x-axis is lag parameter. Lag value, if it is 1, it means you're talking of your neighboring value. If it is 2, you're checking correlation with the after 2 values. So lag parameter is just lag, how much lag depends, how much far your value is from the current value. So it just applied on your entire time series data. So if this is the case on the left side, okay, so you can see that that auto RK is a ki power minus k, okay, and a greater than 1. So this model this kind of behavior, and and a is always greater than 1. Okay, and then and the k is your, this k is your lag, this small k is your lag parameter. So if a ki power minus k and a is greater than 1, obviously, okay, so then what will happen if k increases? What will happen? I think this is a similar case of x power minus alpha. You can see the a, because a is greater than 1 here, a ki power minus k. So what will happen if you increase k? Because his k is 0, then 1, 5, 10, 20, 30. Okay, and obviously this function will more the value of k. What will happen? The more the value of k, the less the value
Probability.
of that ACF function. Okay, the less the value of this ACF function. Okay, but what's on the right side? You can see that in this case, rk is not a function of k, because the lag parameter k itself, because here k was coming as a power, but here k, you should know the difference, that here a was the base and k was in power, but now it's reverse on the right side. On the right side, this k has become itself a power law function. K ki power is equal to a, and this relation h is equals to 1 minus a by 2. Okay, so h is called as Hess parameter. I will talk of more about Hess parameter soon, but you can see that in the right graph, the ACF function is not decaying slowly. At the lag of 0, it is 1, lag of 150, lag of 100, lag of 150, lag of 200. The ACF function still has values. It means that the values in a time series which are 200 items apart are still dependent. The values at time series which are 150 items apart are still dependent on each other. The values at 100 values apart in a time series are still dependent on each other. The values are at 50 uh, at 50 values apart, it is still dependent on each other. And I think that such kind of correlated traffic data, the seasonal trends, I've already shown you in this slide before on. I've already shared the slide. You can see there's such kind of data in which there's so much ACF to question function. You have already seen it, because the values depend on each other. If because if you see this right behavior, it means that the values uh, uh, at lag 50, at lag 100, especially at till 150, they are dependent on each other. It means that you should know the physical interpretation of such kind of graph. If the values are 50 values apart, the items are 50, so if the one value increase here, the other value will also increase, the next will also increase. That means that graph has a very significant interpretation. You must not ignore this graph. Okay, those of you who are feeling difficulty in understanding, I would advise them to just read the definition of autocorrelation function. Because autocorrelation function, it represents, it defines the dependence of a time series, an item within time series, to its neighboring items. Okay, so if your data value increases, and the next value also increases, and the third value also increases, and the 50th value, 100th value also increases with respect to that value, it means their dependence. And if certain value decreases, then the next value also decreases, and the value after 50 points also decreases. Then it means that the first decrease is impacting other degrees. So that's a dependency which is represented by the ACF function. So the ACF function is quite actively used to model dependency in a time series, is or in a single time series. In case of internet traffic, the understanding of this ACF is very important. I would highly advise all of you to read more about the definition of ACF. At NED, we teach this correlation at autocorrelation functions at our undergrad in basic stats course. So I would highly advise you to understand this. So, but in here, I have just written the formula that how we represent such kind of behavior. In case of left graph, you can see that we can model the autocorrelation function decay. You can see that just I can just see that in the left graph, only three one, because at lag 0 it is always 1, because value is always the same at the same point. Okay, at 1 the ACF is something 0.5, and then at lag of 2, I can see here at lag of 2 it is 0.3, and then it's almost negligible. Okay, near 0. So it means that in this graph in which ACF is decaying so much so quickly, it means that traffic, the values, the actual values will here will be quite random. They will be quite random traffic. No value will be dependent on previous values in this case. Only one first two values, and if you pick out in a graph any two neighboring values, they will be appearing dependent on each other. Maybe, but after fourth item, the fourth neighboring value will never depend on the previous values. Okay, it can take any different form. So that causes the randomness in your data set. But if there is on the right side, if there, so after the values, the 150 values apart, the values in the data set which are 150 items apart, they are still impacting each other. So I hope you understand the beauty of understanding the ACF. Okay, so in this, the right graph is more interesting, because in which you have you are formulating, you are able to represent such kind of behavior. How do you write mathematically? Rk is your autocorrelation function at lag k. Okay, Rk is your autocorrelation function at lag k, and you can see that k ki power minus a. So that's you can see that how it behaves. Okay, so a is between 0 and 1. So this is the way which we can model such kind of graph. Okay, so you can see that as the k increases, okay, value of this function will not increase. So I hope you got this modeling part understand. Okay, any question till now? And then correlation and scaling pattern. Long independence affect how variability scales with time scales. Take a traffic time series xn, sum it over block of size m. That is equivalent to observing the original process at a longer time scale. Okay, take a traffic time series at xn, sum it over block size of small m. Okay, this is equivalent to observing the original process at a longer time scale. So how do the mean and standard deviation change? Mean will always grow proportional to the m. Obviously, when you increase block size, because m is your block size, then obviously mean will increase. For IID data, independent and identity data, the standard deviation will grow in proportion to square root of m, and for IID data, the process smoother at the longer time scales. So what is the main thing here? Original process xn. So this is the behavior. So uh, to some of you, this equation might look a bit complex, but it's really very easy. It is just showing that you have a time series of xi. Okay, and you are just creating a new time series from that original time series. Okay, and then you analyze the behavior. I think let me illustrate this equation uh, by my pen here. But before I go there, parameter, and h is equals to half for independent traffic, and then for value h is between half and 1, the traffic is LRD, long independence. So h is the Hurst parameter. And let me tell you some details about the Hurst parameter. That Hurst parameter has been used in case of hydrology. In case of hydrology, they use the Hurst parameter. That in case of river Nile data, that river Nile was flowing, and sometime there was a drought, it never flowed. So they wanted to make a dam. So what they did, that the Hurst, Mr. Hurst, he proposed an estimator to analyze the seasonal patterns in river Nile. So if they are able to capture the seasonal patterns in river Nile or the variation in river Nile, so they can make a dam, so that when there is a drought, then the dam can be useful. Okay, so this Hurst parameter is used to define traditionally since 1950 to define correlation or dependency in your data set. Let me ask you an interesting question. So this is just shown about the behavior of, you can see that h is equals to zero point 0.5, data is very smooth. Okay, h is equals to, this is just, you can see that this vertically it's 10 millisecond, this is 1 second, this is 100 second. Okay, so h is equals to zero point 0.5, it looks like this, 100 second data. Okay, and then you can see that at point, this h is equals to 0.95, looks like this. There's a, you can see there's a strong, some correlation in your data set in this h is equal to zero point 0.5. In this side, you can see these are all appear to be less correlate. But when data is 0.95, you can see the values are impacting the data set. You can see these values decreases, this value decreases, and then increase, and then you can see the dependence in this data set. Okay, there's a dependence in these values, but in case of h.5, there's no dependence. So this is used to uncover the hidden correlation. So I think I'm still not able to convince you about the significance of this equation, the self similarity and the long independence. So it's natural because you are reading this for the first time, and this equation might confuse you. Okay, but I will write down this equation mathematically. But I would like you to tell me about Mona. You are there.
Yes, sir.
So can you tell me what's the dream Prophet Yusuf alayhi salam saw?
Can you repeat, sir?
I'm asking what is the dream? Because in Quran and all the three books, divine books, Bible and Quran, we have a dream in Surah
Yeah.
Yusuf that he saw a dream.
Yes, he saw his brothers
Yes, yes,
um,
there was.
knocking. Yeah, his brothers no, and
No, that's okay.
his father and mother.
That's a story there mentioned. But what about the dream? That's not the dream. He saw a dream. The story has been mentioned in Quran and also in Torah and also in the Zabur, Kitabul Zabur. All the three books they mention the dream which prophet. Anybody else can mention here?
Sir, he saw seven healthy cows
Yes,
and seven unhealthy, like
yes,
very
yes,
starved
yes.
cows.
Great, thank you for telling me this. That the story has been mentioned in detail in Quran and Kitab al-Tawrat and the Bible. That the Prophet Yusuf alayhi salam, he saw a dream that the seven big cows, seven small cows eating seven big cows, and the ruler and the king of that time saw this dream. The king of that time saw this dream. Yeah, am I right?
Yes, sir.
Okay, the king of that time saw this dream that and he saw this dream I think repeatedly. So he was got worried, and the king of Egypt at that time saw this dream that seven small cows eating seven big cows, and also there were some crops similar that. So what was the who can tell me the interpretation? What was the interpretation that because Prophet Yusuf alayhi salam was in jail. He was in jail at that time, so he was asked to come, and then what he said? What was the interpretation?
Yes, sir. He interpreted that there will be drought for 7 years and then
Hmm.
there will be abundance for the next 7 years
Okay,
consecutively.
that's good. That's a great good answer. That because Prophet Yusuf alayhi salam was he was gifted with the divine knowledge of predict of dream interpretation. So the king of that time saw the dream that is seven small cows eating seven big cows. The king got worried, and he asked the interpretation, and nobody at that time could interpret that dream. So then the thing that Yusuf alayhi salam was due to some reasons, all the reasons that why he was put into jail. So okay, you tell the answer to to the king of the time, and I will tell the interpretation. So he answered that in the future there will be 7 years of complete and then after 7 years there will be a great drought coming. There was that the first year will be drought, the next year will be drought, the third year will be drought, the fourth year will be drought, the seventh year will be drought, and they will be, and your all men will suffer. All of the your country will suffer. So when the years of abundance will come, so you will need to prepare for the you can need to prepare for them to keep the storage in that time. So that's why when the year of drought start, so then you use that store to help supply the things. So can anybody here understand how this thing which I'm teaching here relates to this story?
So there's high correlation among the years because once the
Yes,
drought starts, next hard drought, and
yes,
then the
yes.
process.
I think that's great. You got the point. That the things I am trying to tell you, the importance of estimating correlation, because especially autocorrelation, because here we have just a variable year. So if there is an autocorrelation in your certain data like years, and there's a drought there, and the next year will also be a drought, the third year will also be a drought. So you need to model such kind of correlation and need to prepare for such kind of behavior. So the king of that time, he respected the dream, and then for the 7 years he tried his best to store the crops and things, and then the dream came true, and then there was no crops, and the river Nile got completely empty, and all of the there was no rain at that time. And then so there was and then this the largest drought of history occurred at that time, and which humanity remembers. But still the Egypt, the entire world was affected, but except Egypt. Although the Egypt was also affected, but they fall because due to the correct interpretation of the dream by Prophet Yusuf al Islam, that they were, and in fact they were giving the things to the other people coming who were asking for money, who's asking for food, they were giving to them. So that's why this dream got famous. And then the Prophet Yusuf was given the post of, I think, finance minister or kind of thing. So he was otherwise he was in jail. So the idea is here is that this story, why I am telling this story in this class, because I will share you after class finishes, I will share you the book of the title of the book is stochastic processes for long memory processes, statistics for long memory processes, and the author name is Jan Biran. So Jan Biran, and that book has been written by in 19 I think 93, and the new version came in I think 2013. So that Jan Biran author in its prelude and other 2 times or 3 times in his book, he cites this story as the story from Bible, that the dream of Prophet Yusuf to introduce the phenomena of autocorrelation, to introduce the phenomena and importance of why you should not ignore the correlation in your data set. The equation here is there, the m ki power minus h summation xi. Okay, so that variable is being summed over different size of block size, because that small m is block size. So if you sum, you get this new time series, and you see that there after summing, if the correlation exists, then it means that you are in danger. There is a correlation there. But after, because we all know that some summation, superposition, these destroy correlation. But if this relationship hold, that m ki power minus h, and this relationship, that a small m is the block size, if you keep increasing block size and keep summing, and then you find the autocorrelation in the new time series, thus, and there's still a variance and dependence in the structure, then it's a sign of danger. I will show you the graph of such kind of behavior, but I would request that this small equation is a great meaning, that Hertz parameter has a great history behind it. Okay, so I would suggest you to just plot this equation. Use different values of m, use different values of h. This I is your running index, t is your time. So do it, and I think as a master student you can do it. This equation is an historical equation, and you should understand the significance of Hertz parameter. So that's why, so the Hertz so the Hertz, what he did, he tried to model this correlation in his by using his parameter. I will tell you in detail what's the formulation of Hertz parameter in later class, but I would advise that you should understand the significance of correlation, and then its historical thing. And I think that if I tried to give the importance of explain the importance of correlation in this class by using the dream of the Prophet Yusuf, which has been obviously, I mentioned this because the Jan Biran in his book long memory processes, he mentioned in the prelude. Okay, so I will I will even share the snapshot in your mm, and can you listen to me?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, and the same author, interestingly, the same author described the I think in the beginning of the class we were talking about the heavy tail behavior. Heavy tail behavior. I think you all remember heavy tail behavior, in which there were chances of the data in which there are extreme events. Okay, I presented the most recent example of COVID as an extreme behavior process. Okay, but Jan Biran also mentioned the example of another prophet to describe the heavy tail behavior, because they are two now, because you are discussing two type of long independence theory described by the dream of long independence or high correlation has been described by Jan Biran by the dream of Prophet Yusuf alayhi salam. But the same author, Jan Biran, to describe heavy tail distributions, he used the example of another prophet. Can you guess the prophet? I repeat my question. The same author, Jan Biran, he used to explain the phenomena of heavy tail distribution, the heavy tail process, the process with infinite mean, the process is with infinite variance, alpha near to zero. Okay, you all remember the process with extreme variance or rare events. Okay, so Jan Biran used an example of another prophet in which time there was an extreme event. I think now you can guess.
Hazrat no.
Okay, what happened in that Hazrat Nuh alayhi salam period?
Sir, there was a global flood.
There was a global flood, an extreme event in which there was all the humanity died, entire humanity and living creatures except the one who were on the boat. Is it true?
Yes, sir.
Okay, so why Jan Biran used they call it prophet Noah? No. And I think Yusuf, they call it Joseph. They write here, he wrote as the dream of Joseph to explain the correlation. So he used the Noah alayhi salam to explain the process of high variance process, or the process with extremal events. So I think you give the answer that why heavy tail behavior, in order to understand the heavy tail behavior, the flood pattern of that time, because he preached how many years he was there?
950.
950 years he was there, and then in during 950 years there was no flood, and then there one flood came, and then the entire humanity wiped out. So this is an example, just like I should not relate it with the COVID, because I'm not sure if COVID is still not done so much damage, but that flood of Prophet Nuh alayhi salam, that destroyed the entire uh, humanity, and the boat, only the boat was left, and then I think he kept all the living creatures in the boat, so only they were left. So the modeling of, so you see that how these researchers, and then obviously he cited the reference of Bible. He does not, although these stories are in detail more in Quran, and but obviously these are the stories in which all three divine religions, the Jews and the Christians and the Muslims, they all agree on this kind of this the what Prophet Yusuf and Joseph said, and what has been happened with Noah alayhi salam. So that's the thing, and you see that how beautifully they explain and relate, and how they introduce history or religion in case of when they teach this kind of behavior. And I will share the book with you tonight, and then you will see that how the book of Jan Biran got so much citation, and it's the book which has been used by so many researchers, because this area has been and still the book presents a long list of pending such problem. So I will share this book, statistics by Jan Biran. Stats for long memory process by Jan Biran. So that's the, so I hope that by having this discussion you might got some and description interest in the analysis of correlation. I hope you got some interest.
Sir, can you hear me?
Yes, I can hear you.
Sir, in the previous slide where the graphs were shown,
Mhm.
uh, can it be said that the lower the Hurst parameter, the lower the correlation, hence the traffic is smooth?
I can show it here. Can you see the slide now? I am switching. Sorry, this is this slide. Can you see now?
Yes, yes. So
Yes.
in the
So you can.
last graph, where
Mhm.
the Hurst parameter is low, so it can be
Oh,
said that the lower the Hurst parameter, the lesser the correlation, and hence the traffic is smooth.
yes. I think there's something to be careful about. If hash parameter is zero point 0.5, it means that data is uh, completely independent. There's no correlation in your data. And if the value is between zero point 0.5 and 1, then there exists correlation in your data set. If h is equals to very near to 1, then the values are very, very highly correlated. And you must not say that if the h decrease, the correlation decrease, because the case of between value 0 and zero point 0.5, we call it as a negative correlation, negative persistent, in which the process destroy correlation. Okay. And the process destroy correlation. So this is called as negative correlation. So there are very few processes in which processes have negative correlation. I can think of just one example in which a stochastic process tries to destroy its correlation, and that's an example of a doctor. Uh, I think you all have visited a doctor, and if you take an appointment, so what happens if you go to a doctor, a busy doctor, because you have to take an appointment? Otherwise, if you do not control the arrival process, there will be too much queuing, and the doctor clinic will be flooded, always delay. So what they do, they give you an appointment. So and then you come at that time, and then they also queue. But in that case, the doctor PA, the doctor personal assistant, they try to schedule your arrival process. So this is the case when h is less than zero point 0.5. H is between 0 and zero point 0.5. So this is just an example in which, because I'm telling you, because there are I've been asked by many researchers that what is the case of when h value has parameter value less than zero point 0.5. So in books you will see that there's no case, but I can. So this particular case which I have told you, in which the doctor arrival process is controlled by his PA, so in which this is called as anti-persistent of, because the process tries to destroy its correlation, because the doctor PA assistant is trying to reschedule your arrival. You want to come at 5 o'clock, but he will say that, oh, please don't come at 5 o'clock, please come at 4:30. So the expected correlation is destroyed, and the doctor clinic is behaves like a normal clinic. So this is an example. So do remember that if h is equals to zero point 0.5, only in that case the data is completely independent. Okay. When h is equals to between zero point 0.5 and zero point 0.9 point and 1, then this means that there will be correlation in your data set. Your data will be dependent on each other. The next value will be dependent on previous value, and the more the value of h, the more that dependence is strength, because you can see that from the dream of Prophet Yusuf, the dependence strength continued till 7 years. Okay, so that's why. And I am the same. I remember that when I was giving just presentation to some of the stock market guys, they were quite interested to have this discussion. And I have some data, and I'm trying to model that how much stock market can be modeled by Hutch parameter. So I hope you at the moment don't be confused. Those of you who are confused about this discussion, don't get confused. I was just trying to, my main idea today was to put you in a passion, to put passion in you, to understand the significance of correlation and dependence, because there has been a trend to ignore this kind of behavior. Go to the body part of the data where the values are near mean value. People do not want to study the data set which are heavily correlated. Okay, they don't want, because when the data is independent, for example, in this case, actually it's 0.5, you can see the data is independent. Okay, so in this case, the modeling is quite easy. There are so many models, entire stats available to you to model such kind of data. But when H value increases from zero point 0.5 to 0.95 or zero point 0.1, then the traditional statistical model fails. Then you need to get different kind of statistical models, and there are also challenges because such kind of traffic patterns results in long router buffer queuing sizes and packet losses also get increases. So there's long list of impact which I will tell you. Still, don't worry about this. I would just like you to understand the significance of the study of the correlation, dependence, and the rare events. I think after having these two discussion of the which statistics for long memory processes, let me write down the book name because I may forget it. Uh, Sorry, I'm not sure. Oh, I thought I was sharing the slide. I can. This is the title. Statistics for I think you can easily find this book on internet. It's publicly available. So I just write it down on there. So in this book, the both Dream of Prophet Yusuf and Noor Assam incident, it has been mentioned just to explain what, just to explain the importance of the study of correlation and the rare events. So I would rather stop this class now because I have some events to prepare tomorrow. So we will meet next week with a more detailed discussion on these stochastic processes, which are very relevant, which are very interesting. So I hope you got, and I will share the book here just for the sake of, and obviously I will share the book not for your reading because this book is quite advanced book, but just to show you the proof that how Jan Biran used the historical religious events to explain the importance of study of the correlation and dependence and extreme values. So that's why I wanted to, so that you can get interest in this area. Okay, so I will finish my class here. Sorry for long talk. I talk continuously without any break. So, but the good thing is that now I'm finishing class now, but I'm open to any discussion, and I've taken the attendance, and you can leave the class, and I'm here for some time. Those who of you who want to leave the class can leave. I will be here for some time for answering the questions which you want. Okay, so you can leave the class. Classes. So I'm doing the recording off. I'm stop doing the stop recording.